Welcome back to another video. We have already covered how to perform a hypothesis on the population mean when the variance is known. Now, the question is, what can be done if the variance is also unknown? We want to study the population mean, but we have no information on the population variance. Based on what we discussed on point estimators, we know that our best guess is to replace the population standard deviation, sigma, with the sample standard deviation, s, in the normal statistics. Now, the question is if we can claim the x bar minus mu divided by south over square root of n follows a standard normal distribution. The short answer is it is better to identify the distribution of this new statistics. Suppose x1, x2, up to xn is a normal random sample from a normal distribution with an unknown mean mu and an unknown variance sigma squared. The sample mean follows a normal distribution, since each xi follows a normal distribution. The sample mean follows a normal distribution with parameters mu and sigma squared over n as stated by central limit theorem. The sample mean can be later standardized by subtracting its mean and dividing it by its standard deviation to define a standard z-statistic that follows a normal distribution centered at 0 with a variance of 1. As for the sample variance s squared, it can be shown that if we scale the sample variance by multiplying it by n-1 and dividing by sigma squared, the result is a chi-squared statistic that follows a chi-squared distribution with n-1 degrees of freedom. We can use these statistics to form a new test statistics. A t-statistic is formed by dividing a standard normal statistic by the square root of a chi-squared statistic divided by its degrees of freedom. The t-distribution is a probability distribution that is similar in shape to the normal distribution, but has some key differences. As for similarities, like the normal distribution, the t-distribution is symmetric around its mean, which is 0 in the standard case. It has the classic bell shape, meaning that most values cluster around the center and fewer values appear as you move further away from the mean. As for differences, the t-distribution has heavier tails than the normal distribution. This means that it produces more extreme values, far from the mean, than a normal distribution would. In other words, with a t-distribution, there is a higher probability of getting values that are significantly larger or smaller than the mean compared to a normal distribution. The t-distribution is actually a family of distributions defined by degrees of freedom, which is related to the sample size. Lower degrees of freedom, small sample size, results in heavier tails and more extreme values. Higher degrees of freedom, large sample size, looks more like the normal distribution with lighter tails and less extreme values. As the sample size increases, the t-distribution approaches the normal distribution. Here, we are hypothesizing on the population mean when the population variance is unknown. As a result, we are using a t-test for all these three cases. To find the value of the t-test, we need to plug in the values of sample mean, x bar, sample standard deviation, s, sample size, n, and the hypothesized value, mu0. In case A, a two-tailed test, we are testing for deviations in both directions from the hypothesized value. This means that we are interested in whether population mean is either greater than or less than the hypothesized value. To calculate the p-value for this test, we first find the value of the t-test statistic, and then we calculate the probability of observing a t-test statistic as extreme as the one we found, in either direction. If the p-value is very small, it suggests that the observed result is highly unlikely to happen by chance, so we reject the null hypothesis. The rejection region for a two-tailed test consists of both the upper tail and the lower tail of the t-distribution with n-1 degrees of freedom. This is the highlighted area in Part A bottom figure. If the test statistic falls within either of these regions, we reject the null hypothesis. These areas are determined by the chosen significance level. The upper-tailed test, case B, is used when we are specifically testing whether the population mean is greater than the hypothesized value as stated in the alternative hypotheses. In this test, the p-value is calculated by finding the probability of observing a t-test statistic greater than the one we calculated. If this p-value is small, it leads us to reject the null hypothesis in favor of the alternative. In this test, the rejection region is in the upper tail, meaning we only consider whether the t-test statistic is significantly large. If the test statistic falls within this upper rejection region, we reject the null hypothesis in favor of the alternative. The size of this rejection region is determined by the significance level, such as 5%. The lower-tailed test, case C, is used when we are specifically testing whether the population mean is smaller than the hypothesized value as stated in the alternative hypothesis. In this case, the p-value is calculated by finding the probability of observing a t-test statistic smaller than the one we calculated. A small p-value leads to a rejection of the null hypothesis. In this test, the rejection region is in the lower tail, meaning we only consider whether the t-test statistic is significantly small. If the test statistic falls within this lower rejection region, we reject the null hypothesis in favor of the alternative. Again, the size of the rejection region is determined by the chosen significance level. To use Python for hypothesis testing on the population mean when variance is unknown using a single sample, we need to load the t-test single function and pass the necessary arguments. Here, we have a sample of size 30 of height of Italian men. We want to know if we can claim that the average height of men in Italy is not 168 cm at equals 0.01. So, we need to run a two-sided hypothesis. Once the function is loaded, we need to pass the sample data, the hypothesized mean, alpha, and the alternative hypothesis, which here is a two-sided test. The function will return to us the corresponding t-test, p-value, and a two-sided confidence interval by default. If you want to use the rejection region approach, you can use Python to directly retrieve it. Thank you for watching this video.
See you in the next one.